Topic 7. Equilibrium SL Le Chatelier's principle. 7.2.3 Apply Le Chatelier's principle to predict qualitative effects of changes of temperature, pressure and concentration on the position of equilibrium and on the value of the equilibrium constant. 7.2.4 State and explain the effect of a catalyst on an equilibrium reaction. 7.2.5 Apply the concepts of kinetics and equilibrium to industrial process. Suitable examples include the Haber and contact processes. Le Chatelier's principle. When a system at equilibrium is placed under stress, the system will undergo a change in such a way as to relieve that stress. Le Chatelier translated. When you take something away from a system at equilibrium, the system shifts in such a way as to replace what you've taken away. When you add something to a system at equilibrium, the system shifts in such a way as to use up what you've added. Le Chatelier example number 1. A closed container of ice and water at equilibrium. The temperature is raised. Ice plus energy less than, greater than water. The equilibrium of the system shifts to the underscore to use up the added energy. Right. Le Chatelier example number 2. A closed container of N2O4 and NO2 at equilibrium. NO2 is added to the container. N2O4, G, plus energy less than, dash greater than 2NO2, G. The equilibrium of the system shifts to the underscore to use up the added NO2. Left. Le Chatelier example number 3. A closed container of water and its vapor at equilibrium. Vapor is removed from the system. Water plus energy vapor. The equilibrium of the system shifts to the underscore to replace the vapor. Right. Le Chatelier example number 4. A closed container of N2O4 and NO2 at equilibrium. The pressure is increased. N2O4, G, plus energy less than, dash greater than 2NO2, G. The equilibrium of the system shifts to the underscore to lower the pressure, because there are fewer moles of gas on that side of the equation. Left. Pressure changes to system. If the volume decreases, the concentration increases, and there will be a shift to the side with the less amount of moles. If the volume increases, the concentration decreases, and there will be a shift to the side with the more amount of moles. Example, if I increase the pressure, where is the shift? Right. If I decrease the pressure, where is the shift? Left. 2 so 2 plus O2 less than, greater than 2 so 3. 3 moles, 2 moles. Effective concentration. If you add more reactant, it shifts to the right, increasing the formation of product, using up the reactants. If you add product, it shifts to the left. If you remove product, it shifts to the right, increasing the formation of product. If you remove reactant, it shifts to the left. Effective temperature. Energy is treated as a reactant if endothermic equation, and as a product if exothermic equation. If cooling a system, then it shifts so more heat is produced. If heating a system, then it shifts so extra heat is used up. Example for temp changes for endothermic reaction. Heating the below reaction causes the system to shift to the right equals more products, because you treat energy like a reactant. 2 NaCl plus H2 so 4 plus energy less than, greater than 2 HCl plus Na2 so 4. Cooling the above reaction causes the system to shift to the left equals less reactants, so need to make up more. Effective temp change on exothermic reactions. Heating the below reaction causes the system to shift to the left, to use up the extra heat. 2 so 2 plus O2 less than, greater than 2 so 3 plus energy. Cooling the above reaction causes the system to shift to the right, to make up for the lost heat. The effect of a catalyst on equilibrium. Adding a catalyst speeds up a reaction by providing an alternative mechanism with a lower activation energy, thus speeding up both the forward and backward reaction rate. It shortens the time needed to attain equilibrium concentrations. It has no effect on the position of equilibrium, however equilibrium will be attained more quickly. Haber process N2G plus 3H2G less than, greater than 2NH3G del 2H equals minus 92 kilojoules per mole. Mixture's volume is compressed and passed over a heated ion catalyst. Conditions for his equilibrium is critical. High pressure is favorable due to 4 moles on left and 2 moles on right. Increased pressure causes a shift to the left, favoring product formation. This is expensive to do and most production plants will resist compressing gases in terms of operating costs. Compromise will be met. Compromise. This is an exothermic reaction, so low temperatures would be favorable to produce product. Low temps mean low reaction rates, so we may get a higher yield but it will take a long time to get it. Not good for business. A compromised temp, as well as the use of a catalyst, will aid in speeding up the reaction to a more acceptable standard. Typical conditions: pressure between 20 to 100 megapascals, 200 to 1000 atmospheres. Temperatures around 700 K. The reaction is not allowed to reach equilibrium, because reaction rate decreases as we approach equilibrium, and typically only 20% of N2 and H2 is converted. The gases are cooled and NH3 is condensed and removed, leaving unused N2 and H2 available for further production. Animation of Haber process. http://www.absorblearning.com/media/item.action quick equals 128 hash. Animation of Haber process. Ammonia's uses manufacture of fertilizers, ammonia salts and urea. Manufacturing nitrogen used in polymers for the fabrication of nylon. Used in the production of explosives, TNT, dynamite. Contact process. Production of sulfuric acid by the oxidation of sulfur. Sulfur is burnt in air to form sulfur dioxide. S is plus O2G less than, greater than SO2G. Sulfur dioxide is mixed with air and passed over vanadium dioxide catalyst to produce sulfur trioxide. 2SO2G plus O2G less than, greater than 2SO3G del 2H equals minus 196 kilojoules per mole. Sulfur trioxide is reacted with water to produce sulfuric acid. SO3G plus H2O LH2 SO4L. More money, more SO3. High pressure would favor the formation of SO3 in the second step, however it's too expensive. Reactants are compressed to 2 atmospheres to achieve the desired flow rate in the reactor. Pure O2 would drive the equilibrium to the right, however it's an unnecessary expense. Low temperatures, because it's exothermic, would be best, but it slows the rate too much. Compromised conditions. Temp between 700 to 800 K, fast initial reaction rate. The use of a finely divided V2O5 catalyst. Oxidation is done in converters at lower temperatures, slows reaction rate. Overall conversion is 90% to SO3. Contact process animation. http://www.absorblearning.com/media/item.action quick equals 12b. Contact process animation. Uses of H2SO4. Fertilizers, converting insoluble phosphate rock into soluble phosphates. Polymers, detergents, paints, pigments, petrochemical industry, processing of metals, electrolyte in car batteries. Le Chatelier's principle is a memory aid, it doesn't explain why these changes occur. Listen carefully and read over text pages to help you develop further understanding of explanation. http://www.mhi.com/physci/chemistry/essential chemistry/flash/lech17.swf